Kepler's first law of planetary motion states that the planets move in elliptical orbits around the Sun, with the Sun at one focus of each ellipse. The point in the orbit at which a planet is closest to and furthest from the Sun are called perihelion and aphelion, respectively. In reality, the difference between them is nowhere near as great as depicted in the diagram on your screens now. In fact, the orbit of Venus is almost a perfect circle. Kepler's second law states that an imaginary line from the Sun to a planet sweeps out equal areas in equal intervals of time. Now, in the diagram, swept out areas A1 and A2 are equal. The law states that the time taken for a planet to travel from P to Q occurs in the same time interval as when it is travelling from R to S. That is, capital delta T1 is equal to delta T2. Since distance PQ is greater than RS, this means that a planet will be travelling fastest when close to perihelion and slowest when close to aphelion. Once again, the difference in speeds for planets is much less than the difference for bodies that have much more eccentric orbits, such as comets. It's interesting to note that the Earth is at perihelion and travelling at its highest speed around the Sun in early January, the 4th to the 6th in most years, and in theory then our northern winters would be shorter and our summers longer. Now let's talk about Kepler's third law, which states that the square of the orbital period t of a planet is proportional to the cube of its mean distance r from the Sun. And this can be written mathematically as t squared is proportional to r cubed, or that t squared divided by r cubed is equal to some constant. And the table on your screen now shows data from some of the planets in the solar system. The last column clearly shows that Kepler's third law is true for this particular system of orbiting bodies. However, Kepler's laws can be shown to be true for any system of orbiting bodies, such as artificial satellites around the Earth or the moons of Jupiter. The only thing that will change in different orbiting systems will be the constant in the equation, which is going to be called k. It can be shown that k depends inversely on the mass of the central body of the Sun, the Earth, or Jupiter. This can also be written mathematically as constant 1 divided by constant 2 is equal to mass 2 divided by mass 1. Now, in the table you've already seen the value of k is 1 unit, so let this constant be called k1 and the Sun's mass be m1. If we could obtain data for a system of planets around another star, these would have to be in the same units of AU and years, we could deduce the value of K2. Let's say it was 3 units. This would mean that the value of K for this second star system was 3 times greater than the value of K for ours. This would imply that the mass of its central star is 3 times smaller, that's the inverse bit, than that of the Sun. The reason why the time periods and mean orbit radii are related to the mass of the central body is that the force responsible for the orbital motion of satellites and planets is that of gravitation, gravity, and this is an attractive force between all bodies that have mass. So let's talk a little bit about gravitation, and of course I'm sure you know the story. In the summer of 1666, a young Isaac Newton, sitting under an apple tree in his garden at Woolsthorpe Manor in Lincolnshire, contemplating the motion of the moon, and suddenly, without warning, an apple fell from the tree and hit him on the head. "That's it," cried Newton, "I have discovered gravity." Well, I'm sure there might be a little bit of truth in this, because that's how the story goes. What we do know is that Newton somehow made the connection between falling apples and the orbit of the moon around the Sun. Both moved in the way that they did because of the universal force of gravitation. Newton's law of universal gravitation states that every body in the universe attracts every other body with a force that is directly proportional to the product of their masses and inversely proportional to the square of their distance apart, or separation. So gravitation is responsible for creating stable elliptical or circular orbits of moons around planets and planets around stars, maintaining the motion of stars around the centre of our galaxy, causing the Andromeda galaxy to be on a direct collision course with ours, and slowing down the rate at which the universe is expanding. The inverse square nature of the law is interesting, supposing that a comet orbits the Sun in such an eccentric orbit that when it is at aphelion, it is 20 times further from the Sun than when it is at perihelion. This means that when the comet is passing through perihelion, the force of gravity acting from the Sun is 400 times, that's 20 squared, greater than when it was at aphelion. In order to explain orbits, Newton devised a thought experiment in which a cannon, strategically placed on the summit of a high mountain, fired cannonballs at different horizontal velocities, the A being the slowest and E the fastest. And as Newton's cannon fires cannonballs at different horizontal velocities from a high mountain, the velocities of cannonballs A and B are too slow to go into orbits around the Earth. But velocities of cannonballs D and E are too high for a circular orbit. But you can see that cannonball C has the exact velocity to go into a circular orbit. It's falling at exactly the same rate as the Earth curves. Newton was able to show mathematically that the cannonballs would follow different orbits whose shape, circle, ellipse, or parabola, depended on the initial horizontal velocities of each cannonball. Orbit C corresponds to a circular orbit. The cannonball's horizontal velocity is just right, slightly under 8 kilometers a second, to cause the cannonball to fall towards the Earth, but by exactly the same amount that the Earth is curving away from it.